All right, hey guys, how we doing? So as you can see, I'm not with you today. I'm helping move my grandfather. So that promises to be a fun and exciting day. So I'm not here with you, but I've recorded today's lesson for you. So hopefully all goes according to plans. You should have the handout in front of you, lesson 1.6 covalent bonds, and we can get going. So let's take a look. So here we are. And today we're going to talk about covalent bonds. And this is a topic that you should be familiar with, but in case you're not, that's okay. We're going to take our time and go slowly. So the covalent bond happens when atoms share electrons rather than one giving while the other receives. And the classic example of this is the formation of water, one of the simplest covalent compounds. We know, everybody knows, that water has a chemical formula of H2O, 2 hydrogens for 1 oxygen. And so we can imagine what that looks like by drawing it here. And we can draw Lewis structures. So if you check your periodic table, you should know that oxygen has 1, 2, 3, 4, 5, and 6 electrons in its valence shell, and hydrogen has 1 electron in its valence shell. And there we go. And oxygen is electronegative, but in this case, it is not greedy enough. It is not able to steal the electrons outright from hydrogen. Hydrogen isn't giving them up. And so what will end up happening is that these electrons will be shared between both atoms. So this pair of electrons is shared between both atoms. And what that really means is that these electrons actually orbit both atoms. And we can draw it that way, but more commonly we draw these using what we call kind of stick diagrams, or structural diagrams. So more frequently the way we would draw that is like this. And then we could draw, the unshared electrons here. But in this case, the line represents a shared pair of electrons. Oh boy. Oh golly. Sorry about that. Are we still streaming? Looks like we are. Oh boy. I'm having technology issues today. I'm sorry about that. But anyway, we're back, I hope. So this is the way we most commonly draw this, and it represents a shared pair of electrons. Keep in mind that electrons are always shared in pairs, which is to say that sharing will only happen, covalent compounds will only happen, if both atoms have some electrons to bring to the table. All right? What we don't get is situations where both of these shared electrons come from oxygen, because in that case, why share at all? That's not to oxygen's advantage. So understand this, if you understand anything, that electrons are always shared in pairs, one from each atom. So in this case, this shared pair of electrons represents 1 electron from hydrogen and 1 electron from oxygen that now orbit both atoms. And it is this orbiting of both atoms that forms the bond. So the orbiting of both atoms, of both nuclei, forms the bond. All right, so hopefully that makes some kinds of sense. Now, what can we do with that? Well, now that we know what we probably already knew before, that covalent bonding represents sharing, we're going to start to think about the implications of that. Now, I should mention too, this is weaker than an ionic bond. All right, we have this concept next of carrying capacity. Carrying capacity, and the carrying capacity of an atom tells you how many covalent bonds it can and will make. And I'm going to pull up a periodic table because looking at the periodic table will help us to understand what the carrying capacity of an atom is. So we pull up the periodic table here, and looking at this periodic table, we can see the noble gases on this side. And keep in mind that the noble gases are those that have a full shell. They're non-reactive because they have a full shell, which means they are already stable. There's no advantage to them to form bonds because they don't need to gain or lose electrons to be stable. They're already stable. So let's take a quick look at that over here, because it can help us kind of contextualize. So these are already stable. Well, if they're already stable and they don't want to form bonds, then our understanding of the periodic table will give us a sense of what will bond. So the first thing that we should know is that really it is only this section of the table here that can share with one another. Oh, there we go again. Sorry, I keep knocking this cable out, which is profoundly irritating. So I'm very sorry about that. So those ones right there are the ones that are able to share electrons. Everything else on the table has to either give or receive. But everything here, these can share electrons with one another. And only with one another. And once we have a sense of that, once we look at the periodic table and see what can do the sharing with one another, we can talk about carrying capacity, which will tell us how many bonds each atom is looking to make. So looking at the periodic table, fluorine, chlorine, bromine, and iodine, these guys right here, they are one electron away from a full shell. We know that if they were taking electrons, they would take one electron and take a -1 charge. In this case, they're not going to take a charge because they're not going to take an electron, but they will make one bond. So fluorine, chlorine, bromine, iodine, and what else on the periodic table can potentially share? Well, hydrogen can potentially share. So hydrogen can also make one bond. So we'll add it to our list. In the right circumstances, hydrogen will share electrons, and it will make one bond when it does so. Next to that on the table, we can see those things that will make 2 bonds, and that is oxygen and sulfur. And I suppose selenium, but you will never deal with selenium. It doesn't really come up. But oxygen and sulfur come up a lot in sort of regular, everyday chemistry. Of the things that want to make 3 bonds, nitrogen and phosphorus. And of those things that will make 4 covalent bonds, carbon and silicon. And these are basically the only elements that will, as a regular rule, engage in covalent compounds. These are pretty much the only compounds that share electrons. So, knowing that these are the only compounds that regularly form covalent bonds, we can start looking at how we put them together. I want to make a... Oh, that is all in the wrong spot on this note. That's embarrassing. So all of this should be up in the space above. And if, like me, you wrote it in the wrong space, I apologize for that. I strongly encourage you to just kind of slide it on up. And if it's too big, just like shrink it down a bit. Sorry about that. There we go. All right, now another thing to note is that atoms can share more than 1 pair of electrons. So for example, exempla gratia, we could look at carbon dioxide, CO2, which is carbon and oxygen. And we know from the carrying capacity that carbon is going to want to make 4 bonds, and from its carrying capacity that each oxygen is going to want to make 2 bonds. And so how these come together becomes pretty obvious. The way you can make this work is if carbon makes 1 bond here, then 1 bond there, and a second bond here, and a second bond there. And now it's making its 4 bonds. To actually look at the electrons, if we want to draw a Lewis diagram, carbon has 1, 2, 3, 4 electrons in its outer shell, where oxygen has 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. And so we can actually get the formation of a bond here, a bond there, and a bond here, and a bond there. And the way we would draw that, again, is like this. So they can make more than 1 bond. And of course, we usually will put in the unshared pairs of electrons still when we draw that Lewis diagram. And we would call this a double bond. So called because it's making 2 bonds. But it doesn't have to stop there. You can actually make more than 2 bonds. For example, nitrogen gas, N2. Well, we know that each nitrogen has 1, 2, 3, 4, 5 electrons in its valence shell, and 1, 2, 3, 4, 5. And so for this to be stable, and we know this exists, nitrogen gas is all around our atmosphere, it'll share this pair of electrons, and this pair of electrons, and this pair of electrons. And of course, if we map that out, that is a triple bond. So there's no reason to limit it to one bond. You will never get more than a triple bond. The geometry doesn't work for that. You can imagine it would be very difficult for these electrons to interact with those electrons. Now, this is just a scale diagram. But in practice, to the best of my knowledge, I can't think of any example of something that makes more than 3 bonds, though between just 2 things. So maybe that exists. Carbon and silicon, of course, make 4 bonds total, but they won't make 4 bonds with each other. Now, nitrogen gas, as we see it here, is an example of a type of compound we call a diatomic element. Diatomic element. And diatomic elements are the simplest covalent compounds. This is, like nitrogen gas, just the case where things bond with themselves to form stable compounds. All right? And an example of this would be hydrogen gas. Hydrogen itself is not stable. It only has 1 electron in its outer shell. And so a hydrogen gas can find another hydrogen gas that also has 1 electron in its outer shell, and it can form a shared pair of electrons. And we'd write that like this, and its formula would be H2. Hydrogen gas is diatomic. Another example would be oxygen gas. And again, oxygen gas is something found all throughout nature. There's oxygen in the air right now, thank goodness, because we have to breathe it. But it can't just be oxygen atoms, because oxygen atoms have 1, 2, 3, 4, 5, 6 electrons in their valence shell. They're not stable. So they will find another atom that has 1, 2, 3, 4, 5, 6 electrons in its outer shell. Oh, no, should have matched that up. And they will form 2 bonds. And we will get oxygen looking like that. And we give that the formula O2. And of course, up here we looked at the example of nitrogen, and it has a formula of N2. And the diatomic gases, whenever they're found in nature, they're found like this. They're bound to themselves. You will never find H by itself in nature, only H2, because H wouldn't be stable. It only has 1 electron. So the diatomic gases have to pair up with themselves to be stable. I'll remind you what they are. Hydrogen is one of the diatomic gases. Oxygen is a diatomic gas. Fluorine is a diatomic gas. Bromine is actually a diatomic liquid. It's a liquid at room temperature, but the same idea. Iodine is diatomic. Nitrogen is diatomic. And chlorine is diatomic. All right, and we remember this with the stupid word Hofbrinkel, which is dumb, but here's what you need to know. When we do a reaction, if we did a reaction and said chlorine reacts with hydrogen, you couldn't say Cl plus H. That would be wrong, because there's no such thing as just chlorine in nature. Chlorine atoms are way too reactive to exist in nature. There's no such thing as H in nature. That wouldn't exist. You don't see it. If we told you that chlorine reacts with hydrogen, we need to know that the chlorine that's found in nature is Cl2, and that it's a gas. And if we said it reacts with hydrogen, again, we'd know that's a gas. We have to write this. So anytime you see hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, or chlorine in nature, they will appear diatomic. The note already says that, but let's write it again anyways. Anytime you do a reaction with any of these elements by themselves, not in a compound, but by themselves, they must be diatomic. And by diatomic, we just mean write it as 2. H2, O2, F2, Br2, I2, N2, Cl2. Anytime you do a reaction with any of these elements and they're by themselves, they must be shown to be diatomic. Note, that's only when they're by themselves. Don't all of a sudden forget how to make a compound. Note, only when they're on their own. So hydrogen by itself is H2, but that doesn't all of a sudden mean that if you did sodium chloride, NaCl, this doesn't become NaCl2. You can't be like, well, chlorine's diatomic, so that its formula is NaCl2. That wouldn't be charge balanced. Sodium chloride is still sodium chloride. This doesn't make any difference when they're in a compound. It just matters when they're by themselves. All right? And that's going to come up a lot. If I were there right now, I have a thing I do where I would make you all stand up and chant the diatomic elements as if you were a kindergarten class. And I don't know who your substitute teacher is off the top of my head, but if I were he or she, if I were her or him, I would totally make you do this, where I would point to each of these one at a time and I'd make you say hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, or chlorine. And then what I would do is, if you did a bad job, which you totally would because people are always too embarrassed to like get enthusiastic like kindergarten kids and do it, I'd make you do it again and I'd say, everybody stand up. So why don't you all stand up and let's say them together so we don't remember. I'll say, hey guys, what are the diatomic elements? And let's all say it together. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. I'm going to assume that that still sucked, so let's all stand up again and try it together. Chant with me now. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. When you find these by themselves, you have to remember to make them diatomic. But when you make a compound, that has nothing to do with the formula in a compound, just when they're on their own. Everything else that isn't diatomic, when it's in a reaction, can just be written as itself. If something reacts with iron, you would just say solid iron. You could say solid sulfur. You could say solid carbon. Solid lithium. Right? But if you said chlorine, you'd have to say Cl2. It's diatomic. It can't exist on its own. You'll get lots of practice with that, and I will give you a hard time, I promise. Now, covalent compounds are great because they can be anything. We said that ionic compounds are boring. Ionic compounds are just rocks. They can only be put together one way. If you react sodium with chlorine, by the way, what's the formula for chlorine? Cl2, it's a gas. They can only make one thing, because sodium will always take a charge of +1, chlorine will always take a charge of -1, and when you put them together, those charges balance, so it's one of each, so they'll make NaCl. And that's a solid. All ionic compounds are solids, because they're just big, stupid, boring lumps of rock. And then, of course, we could balance this. We could say, well, since this always comes in pairs, we're going to need 2 of those. That'll give us 2 of these. Don't worry about that. You're going to have lots of time to remember how to balance equations later on. The point being, there's only one way to put together an ionic compound. Which makes them boring. They're boring. They're not very exciting. On the other hand, Covalent compounds can literally be anything. You can put them together however you want. Let's just do carbon plus hydrogen. Carbon plus hydrogen could look like anything. Like anything. They can be put together infinite ways. The only rule is that they have to obey their carrying capacity, which means carbon has to make 4 bonds and hydrogen has to make 1 bond. And as long as you follow that rule, you're good. So I could get, in the first example, I could get carbon and it wants to make 4 bonds and hydrogen makes 1 bond. So that is one way to put carbon and hydrogen together. Perfectly reasonable. But I could also choose to put this carbon here and give it a double bond to another carbon. And then that carbon would make another double bond to this carbon, and then hydrogen's there, hydrogen there, hydrogen there, hydrogen there. Is everything following the rules? This carbon is making 1, 2, 3, 4 bonds. That looks good. This carbon is making 1, 2, 3, 4 bonds. So it's cool. This carbon's making 1, 2, 3, 4 bonds. So it's cool, and every hydrogen's just making 1. That's a perfectly reasonable compound. But I could also put it together, carbon, carbon. I could make a ring. And then make that a double bond. 1, 2, 3, 1, 2, 3, make that a double bond. 1, 2, 3, 4, 1. Yeah, I could do that. Is that true? Is everything making 4? Yeah, everything's making 4. There you go. I could put them together like that. These are all, oh, but maybe because we want to have some hydrogen, maybe just here I'll have that one bond to a hydrogen and that one bond to a hydrogen. These are all valid. Covalent compounds are like Lego. You can snap them together any way you want and you can build anything. This is an important concept because you are made of covalent compounds. Ionic compounds are boring. They make rocks. They make lumps of rock because they can only be put together one way. But with carbon and hydrogen and oxygen and nitrogen and sulfur and silicon sharing electrons, you can put them together any way you want as long as you follow the rules. Carbon makes 4 bonds. Silicon makes 4 bonds. Sulfur makes 3. Nitrogen makes 3. That's not true. Nitrogen and phosphorus make 3. Oxygen and sulfur make 2. And chlorine, fluorine, bromine, iodine, and hydrogen, they all make 1. And as long as you follow that rule, you can snap them together any way you want, and you can make really complicated shapes. You can make muscles. You can make hair. You can make eyelashes. You can make eyeballs. You can make teeth. You can make hearts and brains and all kinds of things because you can put them together however you want. Covalent compounds are interesting. Naming them gets more complicated because they are more complicated. Ionic compounds are easy to name. There's only one way they can be put together. Covalent compounds can be put together myriad ways. And so, we need a more complicated system. See, the problem is CO and CO2 both exist. CH4, C2H6, and C2H4 all exist. So, we need a name that give more detail. for covalent compounds. So what do we use? Well, we use a few different things. Some covalent compounds have really complicated naming systems, but the easiest one uses prefixes. We use prefixes. And if you don't remember the prefixes, well, I'm going to give you a minute and ask that you pause this video and try filling them out yourself. So pause, see if you can remember those prefixes and fill them out. All right, I'll assume you paused it. 1 is mono, 2 is di, 3 is tri. 4 can be tricky. You may have wanted to put quad or something like that, but it actually comes from the Latin, and we use tetra to mean 4. 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. And they go beyond that, but this will serve us more than well here. So we put prefixes. So for example, C3H5 would be, well, 3 is tri, so we would say tricarbon, and 5 is penta, so tricarbon pentahydride. So we still go from left to right on the periodic table, though hydrogen's a weird one. We treat it like it's far on the right. It's the only exception. And there's only one other rule, which you know instinctively because you know that CO wouldn't be called monocarbon monoxide. You've never heard of that before. That's not a thing. We just call this carbon monoxide. So there's a rule here, which is we never put mono on the first element. Now, I want to note something. Well, actually, let's take a look at this. Let's try. Oh, I don't know. I'm going to put 3 down here. You try and name them. Let's go C3F2. Let's do. Oh, I don't know. N3H5. All right, so take a minute and name those. All right, I'll assume you've taken that minute. So this would be tricarbon difluoride. This would be trinitrogen pentahydride. And this would be silicon monofluoride. So hopefully you got those. There we go. Now, I want to note something, which is that this system breaks down for complex molecules, because two different molecules can have the same simple name. You don't have to worry about this too much right now, but just be aware that this system you're learning here is kind of a basic system or an introductory system, and there are more complicated systems that we have to use when we get to more complicated compounds. So don't worry about that in this course. You're going to worry about that plenty if you take the 4U Chem. But let's just take a look at an example, just a really simple example. If I said tricarbon heptahydride or heptahydrogen monofluoride. Let's see if we could actually draw that 3 different ways. And you can pause, just 2 different ways. Sorry, that'd be better. 2 different ways. And so you can pause this video and try that if you want. But we'll do it now. So tricarbon tells me that we need 3 carbons. So I'm going to put those in the middle. I mean, there's lots of ways we could do this, but the easiest way is let's just connect those. Now we know carbon wants to make 4 bonds. So we'll do that. So this is kind of our skeleton. And then I know I've got 7 hydrogens, heptahydride. So in this first example, let's just go 1, 2, 3, 4, 5, 6, 7. And then we know we've got a monofluoride, so 1 fluorine, and we'll try putting it there. So that is one way to draw this. So one way it could be built. But is there any reason the fluorine couldn't be here instead? And all these hydrogens. Those are the same basic structure, but they are different. They're not the same. The fluorine's in a different place. So, different covalent compounds can have the same formulas. And we call these isomers. Isomers. Different versions of the same ionic covalent compound. You don't have to worry about it too much right now. Just be aware that it's a thing that exists. All right, that's the end of this lesson. There's some naming practice for you to do here. You can use the duration of this period to do that. My home internet's been wonky, so I hope this hasn't been too impossible to watch. But I hope that note was easy enough to follow. And then after the break, you're going to do a lab prep. And I'll make a little video that talks to you about that. Okay, thanks a lot. Bye.